Good morning, ladies and gentlemen. Welcome back to the next session. Next session will be given by Professor Helen. Okay, let me briefly introduce her. Dr. Helen Lee received her BS and MS degrees from Tsinghua University, both with early graduation and a PhD from Purdue University. Before joining Duke in January 2017, she was an associate professor in the Electrical and Computer Engineering Department at the University of Pittsburgh. Earlier in her career, she was with Qualcomm, Intel, Seagate, and the Polytechnic Institute of New York University. Her research interests include brain-inspired computing systems and neuromorphic design, memory design, and architecture based on conventional and emerging technologies, and device circuit architecture co-design for low power and high performance. She has published a book chapters, and more than 170 research papers in journals and referral conference proceedings. Dr. Lee is the associate editor of IEEE TVRSI, TCAD Asian EAES, IEEE TMSACS, and IET-CPS, and has served on a technical and organization committee for more than 20 conferences. Her papers won 5 Best Paper awards and received 7 more Best Paper nominations. Dr. Lee was the recipient of the NSF Career Award in 2012 and DARPA Young Faculty Award in 2013. And today's topic will be on this emerging technology for this neuromorphic computing and deep learning acceleration, including the emerging technology and hardware implementation. So let's welcome Professor Lee.
Thanks, Robert, for the nice introduction, and many thanks to Professor Lee as well. So I have this pleasure opportunities to come to National Tsinghua University and talk to people over here about our research on neuromorphic computing system designs. So my talk actually is the second part to continue what Professor Chen presented on Tuesday. His talk majorly focuses on software and system levels, and this tutorial is majorly on the technology and hardware implementation levels. So I hope by combining the two tutorials, we can give a more complete picture of the research in our lab. Professor Chen may have introduced our center, the Duke Center for Evolutionary Intelligence. The major research interests in our lab focus on the memory technologies in the storage systems. We actually started this part since 2009, and later on, about 2010, we started working on the deep learning and neuromorphic computing systems because it's very, kind of an accidental chance we moved into this area. No preparation, we didn't think a lot at the beginning. And of course, we're working on the fast, energy efficient, and secure mobile systems. So right now we have about 26 PhD students in our labs. We're going to have like 2 to 3 postdocs in fall semester as well. So if you would like to know more about our labs, here is the website. So in my part for today, I'm going to start with the motivations. Why do we like to working on the neuromorphic computing systems, especially using new technologies on hardware implementations? For the following part, I reorg the sequence of the topics a little bit. So previously, I have IPG in the middle over here. And right now, I reorganize and putting all the all-around-based neuromorphic computing systems together. So I will start with the design concept, and followed by the reliability issues and some very initial solutions we proposed. For the RMs, we all know that the limited precision could be an issue. people prefer to use the device as memory devices. So we talk about that when we just use unit precision or the resistance states, how do we still be able to implement some neuromorphic computing systems and potential issues and challenges. I put in actual several slices on the scalability issues. This is kind of a combination of the software solutions but used for hardware design, used to optimize the hardware designs. This was just published on the back 2017 a few months ago. So I insert several new slices over here. If you're interested, feel free to send me an email and I'm going to share that part slides to you as well. The following two sessions is talking about the applications. One very important application is the graph processing. I'm going to introduce our concepts and architecture solutions, like how do we use Neuron crossbars for graph processing accelerations. And another very important topics in algorithm level, in machine level societies in recent years is the generative adversarial networks. Again, it's essentially to use two adversarial systems and to train and learn from each other. So I also going to present our proposed or some thoughts about how to implement game systems by using RRAM and what is the advantage of this. So after we complete RRAM-based neuromorphic computing systems, I will move to the implementation of FPGA-based deep learning acceleration. Originally, I put this part in the middle because a lot of the thought of the FPGA implementation was initiated or originated from our work on RRAM-based design. And we use FPGA as an emulator to exercise and evaluate some initial thoughts. But I swap the sequence over here just trying to make the topics or the tutorial more smoothly. Let me start from the motivation part. I guess in this week you already heard a lot about the motivations. So this is one example. Dr. Raymond Kurzweil, I think has started as 1998. He talked about the 1990s. He talked about intelligent machines. So at that time, what he did is he tracked the computing powers measured by MIPS and generated curves over here. So at the times, he only generated curve here, and our students pull up more examples. So as you can see, if we follow the trend, the expectation is about 2015, 2017. The computing power measured by MIPS will reach very close to the level of monkeys and the human brains. So 20, 30 years ago, Dr. Kurzweil predicted that, right now in 2017 or very soon, the computer shall be able to behave like humans. Well, we all know we still have a lot of a very long path to it. So what is? Yeah. Why don't we have GPU on there? Actually, we did this probably last year or 2 years ago. So we didn't put the GPUs over here. GPU will be even higher, but still, MIPS-wise, it will be still higher. But just telling the trend-wise, the information we're trying to deliver over here is even the computing systems can perform really fast. We still do not have a sufficient computer architectures and systems to really make intelligent systems like our human brain is. So here is actually the information we're trying to deliver. Okay, so what is the bottleneck? What is the intelligence systems? Even we see that computing speed, computing performance is really, really fast. We're still missing some things. The mystery part factors to enable real intelligent systems. And if we're looking back and seeing what people have done, people really want it, or people really working on, is artificial brains that is intelligent, creative, and self-aware. I think I created this page of slides like 1 or 2 years ago. I think in the past several months or year also, there have tons of discussions about, for instance, the self-aware computing systems, right? So, but if you're looking back about the histories, you can see that people have done many, many works before that. For example, Google's brain simulators. Since we use unsupervised trainings, deep learnings, the systems is composed by 16,000 processors and, with 1 billion connections. And it's used 10 million YouTube videos into trying to learn to tell a human face and create some human faces. IBM Watson also working on defeat humanity in jeopardies. As you can see that the system also made of many servers, and it requires a huge amount of memories. So similar things happens in China and in Japan as well. So if you look into other approaches, people trying to put a lot of processors, either CPUs, GPUs, or FPGAs, to get actually abbreviate the computing powers. So when we're doing this, we have to connect all the computer servers together. And it also requires a huge amount of memories for storage. So the communication becomes another problem. So essentially, when we're talking about intelligent systems, another page of slides on that was proposed by Dr. Hinton. He was a number of program directors and working on the Synapse project. Basically, this is originally what we have. Okay, the personal computing systems, it's used to be wired connected, like desktops and workstations. So in past several years, besides the programming and the fixed operations, what we're trying to make systems to learn. So how to make system to learn? We have to feed the system with a lot of data, right? We have to give them sufficient knowledges. So the example is the data centers and cloud systems. So in data center and cloud systems, it's able to integrate a huge amount of the data. It has to integrate large-scale storage and enable large-scale computing to handle so many data. Another very important thing to enable intelligent system is, so right now we are at the static computing, the offline training, and the virtual world. This is what we have right now. Another approach is to make the computation more dynamic, to make the training or the learning online, and to handle the real world problems or situations. In fact, a lot of approaches has been done on this direction as well. For instance, our mobile phones. I worked for Qualcomm 13 years ago, I don't remember. So I remember like 15 years ago when I worked for Qualcomm, people were joking like, what we can do with the mobile phones. People say the mobile phone was so powerful. Maybe next task is used to shave mask is over here, because people do not know what to do then. But say we are able to use to handle a lot of new applications, a lot of new environmentals, and made our living environment more friendly and useful. So if you're looking into the mobile phones, besides the computing part, besides of the speakers or the phone functionalities, people integrate sensings, displays, wireless communications, interconnect, and also computing at edge. So there are many researching areas in trying to make the training and learning on the mobile systems, or integrate many mobile phones so that it's be able to handle more complex environmental situations. So imagine that we our systems is able to learn to handle huge amount of data. And imagine that our systems can do dynamic, online, and real-world situations. This is what we talk about intelligent systems. Again, people already have a lot of images on this. People already have a lot of expectations, and people already have a lot of solutions for working toward this direction. For example, the IoTs we talk about, robotics, industry internet, self-driving cars, smart grid, secure automotive networks, real-time data to decision, and so on and so forth. So if you're looking into that, there could be more and more applications to discover. So when we talking about this, another problem is, okay, what we can do with the deep neural networks. Okay, deep neural network itself is a not new concept. It was proposed about 1980s. But in the past, I don't know, half decade, there are a lot of up and downs in these areas. I think one of the critical reasons is the computing powers, the limitation of the computing powers. So whenever the requirement of the algorithm exceeding the available computing powers, the society or the progress of the deep neural network or neural network society had to stop and wait for the hardware development progress. So that's looking at requirement from the DNNS societies. This figure shows the ImageNet challenges. The data set of the ImageNet is 1 million images in 1,000 categories. The classification is trying to make the top 5 guesses, as you heard about that many times. So if we're looking back 2010 to 2015, in 5 years, the top 5 errors decreases from 28% to about 3.6%. The complexity of the deep neural network itself, if we measure it by layer numbers, is starting from like a few layers to more than 100 layers. So the complex systems is able to maintain more informations and making the classification more accurate. So deeper models can make lower error rate to us, to people working on the hardware societies. It's indicating a lot of higher requirement on computation powers as well as the storage requirement. So another observation is talking about the data. So when human being learn things, in fact, we actually spend times. I guess you guys are too young to have a baby. I have a boy, 13 years, especially when he was young, you will realize that you have to repeatedly feed him, simple informations. And you have to, he has to spend many, many years to learn the things. Even he is 13 years old, I still feel he is not mature, he's not good on this and that, right? So people can continuously learning through the time. Well, when we're talking about computers, okay, the training, when we talk about training a network takes a week or a month, we say, oh, computation takes a huge time. We want the computer to finish training in a few minutes, okay? So how can the computing system handle that? They have to take a huge amount of data at a short period of times. Looking about the data explorations, I copied this from a website. Every minute, we send over 200 million emails, click almost 2 million likes on Facebook, maybe more dislikes, send almost 300 kilo tweets, and upload 200 kilo photos to Facebook, as well as 100 hours of video to YouTube. I think this is probably even the old data. The trend is data generation becomes it's actually following exponential rate. So data center consume up to 1.5% of all of the world's electricity. Maybe you're not aware of it, but the data center itself has to be large and has to consume a huge amount of powers. So this is what is happening the environmental on our side. Well, talking about computing system again, okay, what is the biggest motivation in past years of our computing systems? What made our computing systems faster, more efficient? In fact, one key factor is the Moore's law. So the technology scales, okay, from, I don't know, 350 nanometers right now, even 1 micrometers. Right now we're talking about 11 nanometers, 8 nanometers, and so on and so forth. But the problem is when we do further scaling downs, generation by generation, the transistor count doubles, but the performance and the power efficiency doesn't increase or improve as expected as the previous trend. So only 40% faster and 50% more efficient, meaning the growth of our computing system is getting slower. We have to look for new solutions in these domains. Higher accelerations for DNNs. Okay, as I said, people already tried all different approaches. For example, for the GPUs, this is probably the most popular solutions in machine learning and the DNNs nowadays. It's fast, extremely high power consumptions. We recently set up the lab at the Duke University. So one critical requirement we ask for is they have to give us very high power supplies, sufficient power supplies. The technician had to triple check with me and say, why do you need so huge power consumptions? Because I guess it means the cost of the department. I don't have to pay by myself. So RPG is another popular solutions, like Microsoft, Baidu, they all trying to explore this. One of the reasons is the power consumption is lower. Professor Yuan was here on Wednesday, and his startups is using this kind of FPGA approach, the solutions for extreme power consumptions. And another advantage, especially for a lot of startups working on IoT or edge devices, is when using FPGAs, its reconfigurabilities provide a lot of flexibilities. So imagine you have an FPGA edge devices for securities. They're able to update the software or the hardware systems, periodically. Well, large companies work on the ASICs. We have some collaboration with the Intel. They're very interested in ASIC designs. So they basically told me that you supply the ideas, but don't worry about the chip design, because we have so many engineers, so many experienced engineers working on the area, and we can do much better chip designs than your small, research labs. So ASICs can supply faster designs for given application or architectures, more energy efficient because everything has been optimized. The key problem of it is it takes longer development cycles. So I guess at current stages, only large companies can afford it. Our labs majorly focus on the novel architectures and emerging devices, because Intel already told me to not working on ASIC designs, right? So there are also a lot of things when we working on the hardwares, we have to think about what happened. So another challenging situation for us, in fact, is the requirement from the outside becomes more and more critical. My area was on the data set designs from also Tsinghua University in Beijing. So I think back to 1990s when I was a student, I only have to handle about the hardware part, thinking about the performance, speed, power consumptions of the designs, the areas, and so on and so forth. For machine learning areas, okay, the design is actually closely related to the application layers. So for the designers, we are not only thinking about the hardware design itself. We also have to learn about the software requirement, the application requirement. So that's why I say environment will make our work more and more challenging. And if you look into that, you may notice that a lot of requirements from software levels versus hardware, what hardware can do are conflict. For example, if you're software designers, if you talk to students at CS, they only cared about the accuracy. They do not care about the network capacities, right? They do not care how to be implemented on the hardwares. So when its model doesn't run or not run fast, they always blame the GPU is not the newest versions. The system is not largest enough. They usually do not consider how to efficiently implement on hardware. But I guess for people from EE background, we can do a lot of better jobs. Okay, so what is the major limitations of the current computing systems? Current computing systems including GPU, CPU, FPGA, ASIC, many ASIC designs. Originally, it's started from Turing machines that separate the CPU for computation and memory for the storage. So the Neuron architectures will have achieved a tremendous success in so many years. But we have to say there are some critical boundaries over here. One of them is, as you can see, the performance gap between the processors and the memories. So the performance improvement of the computing power increase much faster than the data shipment speed. So here already show a huge performance gaps. Another important thing, in fact, is the bottleneck right now, as I mentioned about the data center part, is the power efficiency ceilings. So all this power efficiency measurement, as you can see, it's close to the power efficiency ceilings that 0.001 giga features per watt. And this data was obtained from DARPA. Well, human brains actually have a lot of higher efficiencies. Of course, we can claim that the human brain is in biological structures, and this is in silicon structures. Okay, but this is not an excuse. This is in fact the goal, and we are trying to seeking the solutions to close the gap as close as possible. So, as I said, our group actually originally working on the non-volatile memory technologies, emerging technologies. So we had a lot of discussions and compared about memory technologies. Well, for the spintronic technology versus the phase change memory versus the RM technologies, our lab majorly working on the STT-RAM and the RM. So here's the summaries of those memory technologies. So, in generally speaking, we believe STT-RAM is a lot faster and relatively more stable. So, I believe the STT-RAM is better for the memory architecture, so close to the computing cores. In the RAM, from the memory technology perspective, it's a little bit slower, and but the density is a lot higher, so it's mighty good for massive storage. With the collaboration with the Air Force, we started working on the neuromorphic designs by using RM technology, and we find that this could have high potential in this area as well. So, about the Memristor or the RM has been mentioned many times in this week, so I will go through the introduction of this part very quickly. Memristor, or a lot of times people take it as an RM. It really depends on how do you use it or take it. So I think one of the reasons for RM-based neuromorphic designs is to say the device itself to show a lot of likeness to these biological synapse. Here's the structures. As you can see, the Memristor devices and two terminal devices as the synapse over here. And very important, this is the measurement results. The measurement results shows that the resistance levels actually can continually change. So when we inject the current or the voltage, and as far as it's sufficient enough, the resistance can reduce it gradually or increase gradually. And once we remove the exciting voltage or currents, the resistance states will stay over there. Another very important features over here is, as this is a very simple 2-terminal devices, structure-wise, it can be made as very high density, we call the crossbar structure, or many people call cross-point structures. So what we do, in fact, is if we supply the voltage, input voltage along the horizontal directions, or for instance, these directions, and taking every element over here as a resistive device. So ideally, the current collecting over here will be can be represented by this way. So if you compare the functionality of the Memristor crossbar structure versus the matrix vector operations, you may say this is naturally can realize a matrix operation. So the matrix is represented by the conductance of the crossbar arrays, and the vectors is used, input vectors can be supplied by the current as the input of the crossbar arrays, and the current kept over here is the generated, calculated output vectors. Okay, so this likeness shows we may realize the matrix vector computation in a very efficient ways. And this is actually initialized our works back to 2010. Yeah. You mean the Synapse networks, right? That's actually very, very good comments. In recent years, many people working on the 3D structures of Memristor crossbar and 3D structures of neuromorphic computings. So I talk about 3Ds is one way is just stacking Memristor crossbars vertically. Another way is people talking about the 3Ds have several layers. For instance, we stacking Memristor crossbars, and I talk about the current collection over here. It's essentially they will go to an integrated fire circuits. So many people can talk about that one layer on Memristor for the Memristor technologies, and separate layer for CMOS technologies for the IFCs. And it's used the vias, 3D vias, to supply us the capacitance in IFC circuit designs. So there are a lot of approaches in the 3D stacking a neuromorphic design already.
You can also argue that synapses and neurons are sort of two and a half, right? Because the receiving synapses are one end, neuron, and the other, from sort of like multiple layers.
Yes.
Recently, I made an article saying our brain, the synapse connection is
Yeah. Well, like I said, I don't know how to reach the 11th dimension. Okay. Try to embed it. Maybe people over here can generate more creative ideas. Okay, we can visually see up to 3Ds. We're trying to create on the 3Ds so far. Sure.
Some more feature for Synapse, the cell dynamic.
Yeah, and also, yeah, exactly. It has the capabilities to recover the system. So it has a long-term and short-term recovery. In fact, we read some papers from neuroscience. It's talking about as kids, as a babies, the synapse network connection number is kind of little. So when the baby grows up, the connections becomes denser and denser. So the connection numbers grows up as well. So about teenagers, 12 to 15 years around, it's reached the peak of human lifetime. afterwards, the network connection actually decreases. That's why, my memory is not as good as my son for sure, right? He's still learning, he's developing. But we transfer this information as this. So when we trained neural networks, so in order to feed a lot of knowledges, we have to grow the network. Okay. Once the network developed, and we not expect it, or we say, okay, this network is ready for use, we will find that there are a lot of redundancies in this network. That's why we're able to using pruning or specification technologies. So to remove unnecessary or unimportant connections, to shrinking down the network size, so that we can more efficiently implement on the hardware levels. Okay, so this is kind of a sum thought we observed from neuroscience, and we're trying to apply the philosophies to our hardware implementations. Yes?
The difference between matrix form and the matrix array, like matrix form is sign.
Yes. Yeah, exactly. So this is one limitation we say. So in our initial proposals back to several years, we have to use 2 arrays to represent 1 value. So kind of a matrix A minus matrix B, so that we're able to obtain the negative values. This is one critical limitation of the physical implementations. In fact, another critical implementation limitation is the resistance range is limited. So a lot of times it's made the training on crossbar arrays kind of difficult. Okay. Imagine, because the real values, you can set the data range from negative infinity to positive infinity. But in the Memristor designs, you have to give it a limited boundaries, and that's made the design a bit harder. The training a lot harder. Yeah.
Any other questions?
Thanks a lot for the questions, because I think this is the critical part of my talk. So I'm going to move forward. The beginning part is a little bit slower, but I'm going to move forward to our designs, neuromorphic computing system designs by using Neuron. I will start from design concepts, and just in case you have any questions, feel free to interrupt me. So we start our research by using BSB models, brain state in a box. So, well, a lot of times people ask me, why do you start with this? I think a lot of cases it's just by chance. Well, theoretically, a reason, in fact, is the BSB model. If you're looking at its recall, its recall functionalities is, okay, that's supply an input vector x, okay? And x is doing the match vector calculations first. Alpha is kind of a coefficient, and lambda is also kind of a Bayesian coefficient. And S is a linear output-limiting functionalities to constrain the boundary of the outputs. So once we receive xt plus 1s, we check and compare with xt. We say if the 2 vectors very different, meaning the system is not converged. So we use xt plus 1 to supply, again, kind of doing the iterations. So at time t and time t plus 1s, the 2 vectors very close to each other or identical to each other, we say the BSB model converged. Okay. So as you can see, the core operation of the BSB is the vector matrix operation. And the training process is very unlike of conventional network training processes. Yes?
X in both recall and training.
I use X in what? Yes.
But it appears that X in training, X is an input, and recall X is an output.
Recall
call x is also input. So at time t, xt is the input. It's generate output xt plus 1. T plus 1 is used as a next equation loop.
Well, so, but it's an output. I think this notation's a little confusing.
Yeah, I agree. So it's kind of a serve as an input and output. Yeah, I got you. Yeah, I will go back and check what is machine learning community usually use. I kind of go. This is what they used, and we just borrow the representation here.
Yeah, well, a lot of people have to use it.
Yeah. And for the training process, of course, x is using as the inputs. X minus ax represent the difference of x versus the generated outputs. Okay, and this information together with x is used to generate the delta A, meaning the training, the derivatives of every weight or change of every weight in the matrix. Okay, LR over here represent a learning rate, and this is the upper product of the two vectors. So, well, in the concepts we use this as an example, and we start with how to implement this recall process. Okay, so back to your question previously, you talked about that the matrix can only realize the positive values. Okay, so we use two matrices over here. Initially, the input vector V0 is applied to both matrices. So they parallel doing the computations, and at the end, so they do computation in parallels. So we need two Memristor-based, and then at the end we have to do the subtractions to, in fact, get effective negative values. Well, again, years back we're using summing of m's to form analog values, addition and subtractions. So the Vt plus 1 represent the outputs at t. And at this time point, we have to check if the system get converged, means if Vt plus 1 is equals to Vt or not. So if not, will be supplied back as the input to Memristor crossbar arrays, essentially kind of starting the iteration process. The recall functionality kind of straightforward. The training is a little bit tricky. So when we build the training circuits, one initial task is trying to reuse the recall circuit for sure. And the second part is how we handle the calculation of x minus ax and so on and so forth. So as you can see, this part, in fact, is very similar as exactly the recall circuits. For the trainings, this is the actual part of the trainings. So for trainings, we have to supply the training samples and use to exercise, go through the crossbar arrays and generate outputs. So the error detections is used to measure what's the difference of Vt versus Vt plus 1 and so on and so forth. Well, the difficulty we faced, in fact, is again, if you're working on the software levels, all the values over here, original delta rules, T represent the target, Y represent the new output results, right? And X represent the crossbar values over here. All these values can be traced exactly at the software levels. But in hardware implementations, if you say, okay, I want to precisely read out the resistance level of every device, first it takes a long time, second it consumes huge power consumptions. And even worse, to read out the resistance levels because of the noise, because of the sense amplifier's accuracy limitations, it might not be the exact value over here, right? So we try to bypass this very precise value and related circuit design part. So we modified the delta rules. In modified delta rules, we try to compare the input versus output voltages. So which one is bigger? We use the sign functionality to show, okay, which one is bigger. So it's giving positive and negative. And then we check the sign of input voltage over here, positive or negative. So two sign function nowadays is, computation-wise, is very easy. And every training steps, we giving fixed training process with a fixed training voltage. So the concept behind this, we have to take longer iterations, more iterations to reach the converge. But since all these operations is at higher levels, each iteration is very simple and quicker. So we expect that even more iteration are needed to be able to reach the convergence faster than what we have in the software approach. So BSB model itself is very simple. In fact, during the exercise, we realized the design is very resistant to the noises, and it has a high correlation between merge speed and pattern similarity. So let me show what we do in the application levels. So in application levels, for each set of the crossbar arrays and the related circuits, we use it to recognize one characters. So when we're doing the trainings, okay, we supply the, for example, T over here, different font, regular, bold, italic, Times New Roman, Arabic, and so on and so forth. All different types. We have 50 plus examples and shapes over here, and we use those examples in trainings. So each PIP circuit is only to remember one characters over here. So the system, for example, we want like recognize 26 characters, then we have 26 BSB circuits. For an image supplied over here, it will be sent to all BSB circuits simultaneously. Okay. So when it's gone through the circuits, as I said, we call will take the iterations. We count how fast or slow the iteration takes. Essentially, for example, T goes to T since they are very close to each other. The iteration is a lot faster. But T compared to A, they are very different. The iteration takes a huge time. They may or may not get converged essentially. Okay, so in our designs, we also pick multiple matching patterns for each image. I know this image is really dark and kind of hard to recognize. But for example, for A over here, of course, input A is very like A, and then B is kind of a similar. The N factor is also, show some common features. So those will be picked as the candidate. Okay. And on the system levels, okay, imagine we have the sentences. For each characters we gone through this set of designs, get several characters as a candidate. And then we do the word level confabulations, sentence level confabulations to identify exactly candidates and find out the final sentence combinations. Okay. So in the experiment, I said the BSB is very resilient to the noise, and I will show you one example. This is the original defect-free pattern 8, one of the pattern 8 examples. As you can see, if we talk about the failure rate, ideally, of course, for this ideal pattern cell be 0. And if we consider there are some noises or limitations in circuit designs, we see some failures for the first pick candidates. And if we inject some defects in the pattern, as you can see, we inject a certain number of pattern over here, 30 random points defect over here, and as you can see that we see some fillers for the top pick examples. But for more majority cases, the filler probability is still lower than 10%. Okay, and for the top 3 and top 5, the filler rate is very low, and we are able to recover that at word and sentence confabulation. We also try to use it for different other applications like face recognition, dog viewing, and fingerprint. So the good thing for the BSB model is it's quite reliable. The problem of this, in fact, is it's used one circuit or circuit cells to recognize one pattern. Half your network actually has very similar structures, and you use that for several information storage or recognition. And of course, the rate, accuracy rate is lower than the BSB models. So over here, I'm kind of trying to use BSB models to explain the concept in our designs. In follow, I'm going to talk about the circuit designs. So in circuit designs, there are two couple of approaches. We call this as a spike-based design versus level-based design. In fact, back in 2010, we started with the level-based design because at the time, in fact, we didn't think a lot about circuit design details much. So as I presented in previous page on memristors, our thought is if we're able to supply voltage levels in analog format, okay, this analog values is representing the original data. And it supplies over here down to the vertical path. We collect the currents. Okay, the currents is the summation of the weighted input voltages. Maybe we have to have the circuits down to current to voltage converters, or maybe an DAAD converters needed at the beginning and the output. Okay, so we put DA and ADs at the beginning and the output is because generally speaking, our majority system is still in digital formats. So we're trying to make it compatible to the existing system. In fact, this simulation as well as the paper shows that without talking about the D and AD part, this pure analog operation is pretty fast. Well, the D and AD, if you ever tried circuit designs, is a headache. Not talking about the design complexities, the stabilities, accuracy, everything, the area, power, everything is a headache. In recent years, in fact, people more prefer the spiking-based designs. So spike-based designs, they are all represented by spikes. Spikes in series. For example, this is in recoding structures. In recoding structures, the information is represented by the frequency of the spikes. So giving any period of times, we actually count the process numbers. Okay, so it's also gone through the Memristor crossbars and then integrated fire circuits. The integrated fire circuits is also counting the number of the process. Second approach is closer to biological systems. Power consumption-wise, it's a lot of higher efficiency. So we also working on another version is talking about the plasticity structures. Essentially, we are tracing the timing relations of the input spikes and the output spikes. Okay, STP structures and using the designs. But I guess it's starting from over here into the spike-based. This is kind of recodings and then STPs for the next stage. Any questions? Yes.
Yeah, very good questions.
examples. Sorry for this. So I guess this show, I mean, out of several slices and until we reach that point. So as you can see, this is a spectrum-based design. So I might repeat too many times, but over here, the synapse wave is represented by the conductance in the Memristor crossbar arrays. Well, the input represented by a set of the spikes or pulses, and IFC is used as the output function, activation functionalities. So ideally, computations, we expect the output spike numbers or pulse numbers has a linear relation, so the weighted input signals I we present over here. Okay, our simulation as well as the testing results show it is not true because we have to handle the real design issues. And once we consider the Memristor crossbars and we consider IFC designs, this becomes probabilistic. And I'm going to talk about that in very soon. So let me see a little bit about Memristor crossbar array over here again. So those images from HP Labs, our collaborators. This is actually the device structure of Memristor, and this is the IV curves. So as you can see, the IV curve essentially can translate the resistance levels. Well, in our papers, we kind of discussed many types of cell structures. Of course, the most efficient way is 1R designs. This is, the high density crossbar arrays. S1R from device level is a newer approach because it's still two terminals, so it's still be able to achieve very high density. The design of S is critical in device process areas. I'm not expert over there. But I think people are still trying to overcome the technical issues. Many groups like our collaborator at HP, UMass, Michigan, they already achieved very good results. So the critical issue over here is on and off of the S may take longer time. And the transition of S on and off is critical in the design. So previously, we actually take an easy pass. We take to 1T, 1R. T transistors has better controllabilities. But of course, the area-wise is much larger. And here shows the front-end and back-end structures. We use kind of a UMass and HP devices, and they put it on back-end devices. So they made CMOS first, then iron devices on the top. So for 1T, 1R designs, multiple conductance levels can be maintained pretty well, like the Merman results showed over here. And the Merman results also show the endurance of the devices as well. We use integrated fiber circuits as a neural functionalities. Let me finish this part first. So in these designs, as you can see, we have a current or the voltage of the vertical directions. In the F6, we have the integrated capacitor over here. This kind of accumulated current or the charge over here. This is a current mirror, as we all know, right? And we have two cascaded drivers to generate a high voltage at the end. This is kind of feedback loops, and feedback loops is used to control, kind of boost the voltage over here. And this path actually control on and off, discharging of the capacitance. So this is in fact, the simulation results. As you can see, the output V wide over here, it increases first. Once it's reached threshold voltages, it's the V out actually generated. This is kind of a better shape the process. And meanwhile, you can see that we kind of turn on M13s, so we have a discharge over here. So in this layout, as you can see, kind of one half of the area was consumed by the capacitor itself. This is very kind of key have the area of 300 micrometers on 130 nanometer technologies, but half of area is consumed by the capacitors, and we have to try our best to reduce the size of the capacitor already. So as I mentioned, some of my friends, Professor Yang Yi, she recently moved to Arizona State University. They actually trying to utilize the 3D vias as the capacitor, so the design areas can be reduced. Of course, for security designers, next question we will ask is how is the variabilities, reliabilities of those capacitors, and so on and so forth. So for our designs, the IFC can reach a rate of up to 500 megaspikes per second. This is the highest speed we can reach. Energy consumption is 0.48 picojoule per spike, because our design goal is to reduce the power and energy consumptions. Well, yeah.
The process, special process.
No, ARM was made by HP is separate. Yes, differently. Actually, we haven't been able to, in this versions, we haven't been able to integrate the two parts successfully. So all the control circuits, fab is separately, and HP has their 1T1R crossbar separately. Our design goal is, by the end of this year, we could integrate version 4 fabrication. So back to your questions over here. Computation accuracy. Computation accuracy, the expectation is the actual spike numbers and the sum of product computations shall follow in linear direction. And this is actually the real curve we obtained. This is not linear for sure. But it's kind of follows some certain trend. As you can see, when we increase the overall pause period, okay, it's generating more pauses, okay. And another observation is if you're looking at the exactly same, sum of product, the pause numbers could fit like 1 to 2 difference over here. This is because the summation over here represents controlled by conductance and also current. Imagine you have a high current, small conductance, and then you probably could see some shoots on the capacitors and so on and so forth. So there's some variations. So we do feed curving. The curve feedings and curve feeding can be represented by this ways. So essentially, we find out T0 is limited by IFCs, meaning our IFC have the maximum performance speed. So that's to say, the product goes to this place, it couldn't generate more spikes because it's reached the maximum speed of the IFCs. And the linearity part actually is limited by Memristor crossbar arrays, so it also generates variabilities. But generally speaking, it's follow the trend, and then following works, we try to utilize software level skills to overcome the variabilities on this level. Here is the simple examples we had for just the simple digits designs. So in this design, current designs only shoot for 8 resistance levels from 10K to 1 mega ohms. So we have to again use 2 Memristor crossbar arrays. Essentially, we have this 2 columns to represent 1 essentially value. So this minus this represent 1 value. And of course, the maximum ones will be represented as the final results for this example, for this design. Can I extend a little bit, or shall I stop over here? Okay, give me several minutes. I will go through this quickly. So, pattern recognition. We try different cases, simple cases for binary digits, and MNIST for the more complex design. This is 2-layer designs. you asked about the granularities. So I show several examples here. So this figure shows when we increase the pulse width, as you can see, the failure rate for the simple examples reduces. So for the simple cases, as you can see, of course, 10 nanosecond pulse is not sufficient. 20 to 30 to 80 doesn't show huge differences. So for every given applications and designs, we expecting and required pulse widths. For this one, we choose about 30 nanoseconds as our target designs. And this one actually shows the difference starting from ideal designs with ideal weights like all analog formats, ideal output, after considering only 8 conductance levels. So visualization of the weights made design worse, the recognition rates worst. I mean, without any optimization skill at the top levels. And of course, the spike outputs also degrade the performance. Well, we have the design structures like, I introduced it previously, and this is one of our designs. We use it for before designs of, this example. We also have two layers multi-level designs for missed examples. Here is the chip tester results. For this case, top is the post-layout simulation results. Of course, it's passed, otherwise we wouldn't send for the fabrication. Measurement results kind of random. I pick a case over here. It shows that output follow 1, 2, 3, 4, 3, and 0. This is supposed to be 5, and it's recognized as 3. So statistical-wise, there's no defects on the patterns. Relatively, we got about 90% of recognition rate. It's still not 100. But when we inject the defects, what we find is 5 degrade really fast. The other patterns are relatively better. So one of the reasons, in fact, is 5. I don't have 5 over here is share a lot of common features with the 4, with the 3, with the 2s. So if you're looking at the circuit simulations, the margin, the output 5 compared to others is a lot smaller than, it's very small. So any variations on circuit designs, environmentals, could make recognition fail for the pattern 5. That's the case for, unfortunately, for our design. So I guess I can stop over here, and afterwards I think we'll talk more about our work. Thank you. No, this is not comparable to conventional CNN for sure, because conventional CNN have this convolution layers. It's captured the features a lot better. But our latest measurement from APs for 2-level MNIST, Memristor measurement results can obtain about 90% accuracy for MNIST data. Yeah.
Okay, so let's have a lunch break, and please go back 1:30.